vocabulary set.
Okay, so next presentation is the last presentation of this session. So 5C4, the presentation title is the guidance map transformation for writing control in patch-based style from Muhammad Arief and Hideki Kodo sensei and Mikami sensei.
Okay. Hello. Hi everyone. My name is Muhammad Arief from Tokyo University of Technology. Today I would like to present my research with title Guidance Map Transformation for Lighting Control in Patch-Based Style Transfer. This research is collaborated with Hideki Kodo from Tokyo University and Koji Mikami from Tokyo University of Technology. So the goal of our research are to get a style transfer of high frequency detail with lighting interaction. And the second one is to investigate the effects of the guidance map distribution variation to expand the range of resulting animation, such as we edit the distribution with the surface normal factor transformation, posterization, and also smoothing effects. And then to make all of you understand easier to what I mean, this is the result video of the research. This is the baseline result, original mapping. This is the style transfer result with vertical interaction. So this is if we edit the light area, and we can get the effect brighten of the style transfer. If we segment the guidance map, we can get like uniform lighting. If we smooth the guidance map, we can get like smooth or rounded lighting. And we test in the various example. Yeah, we can see the style transfer is temporary coherence across the frame. And if we animate the guidance map and animate the character also, we can get this kind of animation. Yeah, the animation is stable, and we can incorporate as many animation. So this is just a simple rotation effects. Okay, so the background is the current style transfer, especially patch-based transfer, can transfer high detail of style. This is from the Skyra et al. 2019. They can do the style transfer in fast, but it cannot animate the stroke that transfer to the target. Sun-directed works is a basis for a style transfer, such as work from Sloan et al. From 2001. They can do transfer the style from example guidance such as sphere to the 3D objects, and we can see this technology has been used in various software. This technique called MATCAP in the ZBrush or Maya or soft image. And this research is worked well with the low frequency details, such as in the pictures you can see that the style in the sphere guidance is transferred to the 3D object. It can transfer well into the object, and as we can see, the exemplar can actually transfer into the model. But in the other hand, it doesn't have the lighting interaction, so that the target only have a static stylized shading. And also, we are using if we are using a 2D texture example which contain high frequency details such in the picture, so the result will have artifacts which leading into not smooth transfer, such as this one. So yeah, so work from Skora et al. 2019 can do really job of transferring the style using cluster-based algorithm. It can also transfer with high frequency detail, but there is no patch animation toward the transfer to the target, so there is no lighting interaction. So this is my method overview. So we begin with a 3D model, 2D textures, and guidance normal map. Using the lead sphere extension from the et al. 2013, we project the 2D texture style, the guidance map, normal map into 3D model, and then we manipulate the color distribution of the guidance map using surface normal vector transformation from arief et al. 2014, K-means clustering for posterization, Gaussian filtering for smoothing, and then the guidance map is animated by applying a rotation matrix to the normal vector encoded into the 2D image as a transform guidance map. And finally, we synthesize the stylized appearance with high frequency details based on the guided patch-based style transfer map using the Skora et al. 2019. Yeah, so we implement our method in MATLAB for guided patch-based transfer, posterization, and smoothing for the normal map. And we implement our method in Maya for providing a convenient tool for normal rotation and local editing. And this is to make a guidance map creation. So in this, we use the lead sphere extension projection by Ture et al. 2013. So basically, we project 2D texture into 3D model. And in this, we use a 2D texture, so with the normal map color into 3D model, and we can get kind of this 3D model with the normal map as texture. Yeah, so the original normal map NC is undergoes to the transformation. The original normal map is transformed using the rotation matrix, resulting in the transform normal map. So this rotation is sorry, maybe I missed someone. Had this one. It should be this one. So this rotation matrix is constructed through common Euler rotation in XY order without Z-axis, influenced by angles theta and phi respectively. In our method, the shape rotation matrix R, Ry, and Rx is applied to each normal rotation across all image pixels. So if you can see the video, you can get some animated guidance. So the local editing is achieved through the region control by modifying the z coordinate of the normal. So it happened in this editing. It happened in the 3D environment. So we want to incorporate the local editing control for this vector using this equation. And then user can adjust the IL for the intensity and R for the radius of the region. Yes, the reason that's why we added the guidance map into posterization is to investigate the effects of segmented normal maps on the style transfer process. And it also can simulate the low polygon effects for the target object. And we did this posterization effect by segmenting the guidance map using the k-means clustering. And also, we are particularly interested in investigating the extreme values of the smoothing of the guidance map by applying a guidance blur filter with a large kernel size, and then we can create a very smooth guidance map which leads to reduce the number of the unique region. And then, so it is the patch-based style transfer process. So with the given rotated normal map, and then we apply the guided patch-based style transfer similar to the style build. So this transfer is performed separately for the low frequency base layer and the high frequency detail layer, as illustrated in the figure. So we decompose the exemplar, this one, into the base and the detail, and we use slit sphere projection to create this one, and we make and then we use the Skywrite All 2019 style grid for creating this one, and then we compose both two images to create this one, so it can preserve both smoothness and high frequency details. So this is the result of the guidance map distribution control with patch-based style transfer. Okay. So without any editing, just rotation matrix, so we can give the lighting effects with high frequency details. And so we can see in the leg area, so the times we can give a fake effect to the leg. So it demonstrate the local editing of the normal map. The transfer normal in the leg area is result in either can increase brightness in the low frequency features like this one, and the high frequency patterns also vary by referencing the brighter samples without any deforming artifacts. In this scenario, the modified normal distribution can apply to the illumination chains. So we can add like a fake lighting to brighten specific location. So in the posterization case, so the normal map is segmented into the flat region, resulting in the uniform lighting in the base layer. Meanwhile, the detail of the detail transfer animates the high frequency patterns like texture translation to the shift in the cluster center in the reference point. The synthesized patterns are preserved without deforming artifacts to patch sampling. So in contrast, the smoothing tends to blur the surface detail, resulting in the rounder and larger cluster, and this operation creates smoother lighting in the base layer. And some discussion of it. Yeah, so the base layer transfer process through the lead sphere dynamically animates the primary shading effect by incorporating extracted low frequency components. This approach address the limitation of the lead sphere, like we show in pictures, to the base and detail layer separation, like we can successfully reducing the high frequency patterns. And our system can generate diverse staging style using various media such as stroke effects, traditional hedging tones, and dot patterns. And the system can maintain stable motion even with different high frequency characteristics. And with the appropriate separation with the base and detail layers, we observe that the high frequency patterns are transferred without deformation and without noticeable stitching artifacts on the boundaries of the region in the result. Given that the most color variation of the shading are input in the base layer and the small variation in the detail layer seamlessly connect different regions, this strategy is valid, is okay for many types of different regions as shown in the figure. And the separation process controlled by theta, standard deviation for Gaussian filter, is crucial parameter to determine the extent of smoothing applied to the base layer. This parameter significantly influence the final transfer result as is illustrated in the figure. Like a small value of 0.00002 leads to the presence of the high frequency patterns in the base layer. So this pattern might cause deformation during the base transfer process. So we can see like some deformation artifacts. And the other hand, our large value of this one can include the base layer transition on the detail layer, resulting in the segmented transfer region like this one. So we must set appropriate value like 0.03 to achieve like stable animation, like in this one. So yeah, in this context, we can the patch scale parameter acts as a critical factor to controlling the sampling granularity as the sampling from the style exemplar during the transfer process. So it edit the spatial distribution of the exemplar pixel that contribute to the stabilization of the target image. So we can see it's more coarse, more fine, and just like the finest one. And yeah, this is like the animation for the view transition. We can produce stable motion in the detail layers even during the normal shape change. Yeah, so the conclusion is we combine the lighting control with guided path-based style transfer and examining the influence the normal map distribution on high frequency details, such as material representation is crucial because material is crucial for artists to create many styles. And the method is introduce the possibility of sampling in the reference in area with significant difference in normal guidance. And we need to carefully examine the parameters to ensure the stable animation. Hi. Thank you.
Thank you for your presentation. Is there any question or comment? Okay, I have a question. So I think so style transfer is very so subjective method by each people. So how to evaluate style transfer, which one is good or bad? So some estimation was some evaluate method to style transfer.
Okay, thank you for the question. Yeah, so basically, so my method basically It's different from the neural networks like that appears recently. So like my method is the example based method. So we can like directly like how to say transfer the style what we want to the object. So we thought because in the neural network or deep learning, like the system like how to say need to think which one is the area need to be transferred. But in using example based like past based, so we can like Sonomama like just directly transfer to the region.
Okay, thank you. So, and I have one question. Can you also apply to some dynamic object? For example, some animated characters?
Yes. Yeah, so like in this example, actually, I just animate simple rotation.
Yeah.
So like we can.
For example, some arms are moving or in the
Yeah, so we can animate.
Okay, thank you. Is there any question or comment? Okay, okay. Thank you for your presentation.
Thank you.
So it's a time to finish these sessions. Okay, so I end this session. So please give a round of applause for all speakers and all questionnaires. Thank you so much.